Hi, I'm Darshana Sharma, and here's my presentation on Lab 6, Magnetic Braking with Faraday. The purpose of this lab was to collect observational data of a magnet falling through a conductive tube aluminum foil, and using this data to model the magnetic tube interaction computationally. And then from there, we compared the computational predictions with the observed data. And this also in this lab, we also observed and applied Faraday's law. And improving my results with that, I received an experimental result of 1.5 seconds and a computational result of 2.02 seconds. The fundamental principles used in this lab are Faraday's law, which describes how a magnetic field interacts with a circuit to provide an EMF. We also use Biot-Savart law, which describes magnetic field generated by a constant electric current. We also use Ohm's law, which is V equals IR. And we also use the concept of magnetic force on a wire loop, as this is similar to our system. And then we also use Newton's second law, which is F equals ma, and Newton's third law, which is that every force has an equal and opposite reaction. And this helps us understand how the magnet behaviors changed when it drops into the aluminum tube. So in this experiment, we use a smartphone, bar magnet, aluminum foil roll, and meter stick. And the system is the magnet and aluminum foil tube, and the surroundings is the earth and everything else. And we also have a magnetic dipole moment of 2.54 AM squared, which we got from lab 3. So some assumptions are that air resistance is negligible and that there's no external magnetic field, and that gravity and magnetic force are the only acting forces. So for the procedure, we used a magnetometer app to determine the north and south ends of the bar magnet, and then we held the aluminum foil tube vertically and dropped the bar magnet in and recorded the time it took for the bar magnet to go through the entire length of the tube. So here for all 5 trials, we received an average of 1.5 seconds of the time it took for the magnet to go through the tube. And here are my foil dimensions and the bar magnet mass. And what we observed is that the magnet falls slower in the aluminum tube and compared to if the magnet was free falling. And this is because the magnetic force of the induced current from the aluminum tube moves upwards to reverse the change in flux, which ultimately slows the magnet down. So for my computational model first, I like isolated my constants, so resistivity and gravity, and then I initialized my graph, and then I created a tube of aluminum foil so I could model it in my computational model. And then this is still making my tube and like isolating each ring of the tube because this is important to understanding how the current goes through the aluminum tube. And then we created the bar magnet, and then we created a function to calculate the magnetic field of a bar magnet and then to calculate the magnetic flux in this experiment. And then we calculated the gravitational force of the magnet using these functions and then computed the typical magnetic field at each ring. So this is helpful in understanding what happens at each ring when the magnet does pass through the aluminum foil tube. So then we calculated the magnetic force of the magnet, which is F of gravity times F of magnetic, or this is like the entire net force. And then we plotted the graph of velocity and time. And so this is on the left, this is what the model looks like when it's completely run. So the blue end represents the North Pole, and the magnet passes through the top to the bottom, which is why it's resting at the bottom. And in my graph, you can see that my time in the tube is 2.02 seconds. And you can my graph is shaped this way because this indicates that there's more than two forces, more than just gravitational force acting on the magnet. As if it was just gravitational force, it would be linear plot. Whereas in this case, it shows that the velocity slows down, which indicates that the magnet is slowing down in the tube. So here on the left is what it looks like when the magnet is passing through the tube, the south end. The red end is the south pole, and the blue end is the north pole. So the magnet just falls from the top to the bottom, and it rests at the bottom, as you can see, and the blue end is just indicated. So my experimental time is 1.5 seconds, and my computational time is 2.02 seconds. And the graph shape indicates that there's more than one force, as there is a force of gravity and magnetic force. And I found a 25.7% error in my experiment. And some potential source of error could be inaccurate measurements of aluminum foil tube, bar magnet dimensions, and timing how long the bar magnet took to go through the length of the foil. There's also an inaccurate assumption of negligible air resistance and friction, as these things are in real life, and other magnetic fields from magnets around the room could potentially have caused interference. So if resistivity of the conductor were reduced, the current would increase because resistivity and current are inversely proportional, as seen in Ohm's law. So this would mean that there's a larger eddy current in the magnet, which creates stronger magnetic fields that work against the charge of the flux, which would oppose the magnet's fall downwards and slow it down. And if holes or slots were cut into the tube, they would decrease the amount of current rings that make up the tube, which would decrease the opposing magnetic force generated by the induced current. This would increase the rate at which the magnet falls and speed the magnet up. Thank you.